In the last video, we talked about Cauchy's formula, and in this one, we'll be talking about some of its implications, some of these very powerful implications that we'll use in later videos as well. So a note about this video is that we won't be doing a lot of proofs of the theorems for the simple reason that a lot of the aspects of the proofs are things that we've already seen, and it would just take too much time. For example, this proof itself, theorem A, the proof involves things like the integral estimation formula that we used once or twice already, so it's not really going to be instructive. So nonetheless, let's just go straight into the theorems. So the first theorem, theorem A, states that suppose f is analytic in a domain D, nothing new, and z0 is a point of D. If this disk, so often when something's written like this, it's a disk. So if this disk centered at z0 with radius big R lies in D, then f has the power series f of z equals sum from k equals 0 to infinity of a sub k times z minus z0 power of k, valid inside the disk. Furthermore, a sub k, these coefficients right here, equal 1 over 2 pi I times the integral over gamma f of w over w minus z0 to the power of k plus 1 dw. So this seems very complicated right here, and we won't worry too much about that in this video. The only comment I have to say on this is that this is why this is an implication of Cauchy's formula, because if we did do the proof, then we would see that Cauchy's formula leads us to this integral right here, which you see many parts. We have the w minus z0 to the power of k plus 1. This bottom denominator and the numerator are all straight from Cauchy's formula. Same with the 1 over 2 pi I. So now the next thing we should talk about is what this gamma is, because we didn't define it yet. This gamma is a positively oriented circle. So this is a circle now, with small r is between big R and 0. So it's still a positive number, smaller than big R, but it's just a smaller radius. So now, as we always do, let's try to make sense of this theorem through a picture. So let's see, f is analytic in a domain D. So I have this green domain, it kind of extends above and below. It doesn't really matter how big it is. So we have the green domain D, and it says if we have this disk which lies in D. So do we have a disk that lies in D? Yeah. So the brown dotted line I drew up there is the disk. So that disk does lie completely in D, and I've labeled it as modulus z minus z0 is less than big R. Then f has power series f of z equals this valued in the disk, and this is the important part of the theorem. This says that if these two statements are true, if f is analytic in the domain D and this disk lies in D, then we can just straight up express f of z as a power series, which is great because in the previous video we were trying to express f of z as an integral. Now we're trying to express that as a power series, both of which are powerful things to do. So that means that within this disk, we can express f as this power series right here. And these coefficients are given by this, but notice something else. If you go back to our series video, these coefficients are also given by something else, which I've written down here in blue. So this video right here just showed that these coefficients are given by this nasty mess right here. But we showed a much easier form of the coefficients. They're also given by the kth derivative at z0 divided by k factorial. So go back to the power series video of complex numbers to see why this is true. And since this is just any other power series now, it's not special. It's just any other power series. This holds true, but also this holds true because of this theorem A. So we'll be using this form predominantly throughout this video because it's simpler to use and takes less work, but this form is important, which we'll see in future videos. So again, gamma is the positively oriented circle, so it's going to be modulus w minus z0 is equal to r, so small r, and small r is going to be something that's still positive, but less than big R, and we can always find a number like that just because numbers, that's how they work, there's always gaps between them. So the gamma I've drawn here is this pink circle right here, and we have positive orientation, right? So we want the inside to always be on the left, so it's going to be counterclockwise direction. Those orange arrows show which direction we're going, counterclockwise. And that's all true, so then we have f of z equals this power series valid inside that disk. Okay, so the next thing we'll do is talk about a corollary of this theorem. A corollary is if f is analytic on the domain D, okay, then so is f prime. And that's the corollary itself. The next sentence is just an implication. So let's say f is analytic on the domain D, just as it was on the previous side of this paper. Then so is f prime. Let's give f prime a new name. Let's call it g. So a new function g. So then so is f prime or g. Now g is analytic on the domain D, right? Because we just by this what's underlined here. So g also satisfies this criterion. Now we can say if g is analytic on a domain D, which it is, then so is g prime. So g prime is also analytic. And what is g prime? G prime is f prime prime or f double prime. So that means if f is analytic on domain D, then so is f prime, then so is f double prime, so is f triple prime, and so on infinitely. So as it says here, so f has derivatives of all orders, all analytic on D. And we can just give a simple definition of why. Why is because in a disk within D, f of z is represented by a power series, right? So it's kind of piggybacking on theorem A, because theorem A says that if f is analytic on domain D, and we have this disk which is lying in D, then f has a power series. And once it has a power series, we can apply everything we know about power series of complex numbers that we learned in the previous video. And one of the things we learned was that if f has a power series valid in this disk, then it's infinitely differentiable in that disk. We can take the derivatives of all orders and they'll all exist. There'll be no problems with that. So that's a very powerful theorem as well. So now before we go on with theorems, let's do some application. Let's do an example. So here's the task. We want to find the power series for f of z equals big log of 1 minus z. So remember, when we have this big log, it's the principal branch of the logarithm where argument goes from negative pi to positive pi. Okay, so now let's go ahead and just try to do it. So we have f of z equals log of 1 minus z. So now let's take the first derivative. Well, that's going to be given by negative 1 over 1 minus z, or negative 1 minus z to the power of negative 1. We take the second derivative, we get this. We take the third derivative, we get this. We can go on and on and on, but let's try to find the pattern, because that's going to be the main point during our examples. You're going to try to find a pattern for the derivative. Once you do that, your work is pretty much done. So notice that the kth derivative of z, so again, f is the function big log of 1 minus z, is given by negative quantity k minus 1 factorial over 1 minus z to the power of k. And this is true for k equals 1, 2, 3. It's not true for k equals 0, because if we want f 0 of z, which is just f of z, then it's simply just given by log of 1 minus z. But for all the other derivatives, first, second, third, and so on, it's given by this form. Let's just test that. Let's say we wanted the third derivative, right? So let's plug in negative. So k is now 3, so it's going to be 3 minus 1 is 2 factorial. So we would have negative 2 over, and we would have 1 minus z to the power of k is 3. Is that indeed the third derivative? Yeah, it's negative 2 times 1 minus z to the power of, here we go, negative 3. Okay, and this is the same thing as we have right here. So next thing we want to do is try to find the disk in which this is true, because remember, this theorem A has two parts. Suppose f is analytic in domain D, and so we want to try to find this domain, and we also try to find this disk which is lying in this domain. So to do that, what you usually want to do is find where this thing breaks. See if this has any points where it's not going to be differentiable. And it's easy to see this one. If we have z equals 1, then we have big log of 0, which is undefined. For every other z, this should be fine. So now let's write where that is. So z equals 1 is right here. So we cannot have our domain being part of this. So let's choose for our domain the disk centered at the origin and with radius 1. And this is going to be an open disk, so it does not include this z equals 1, which is good because that would cause it to break. It includes everything on the inside, and this is going to be our domain. So this is unique because usually our domains are big, but right now our domain is pretty small, relatively. So now what are we going to do? Now we want to find now here's something interesting we're going to do. We want to find this disk which lies in D. It turns out that disk that lies in D, we're going to choose D itself because D is a disk. And D lies in D, if that makes any sense, because this disk itself lies inside itself, because any set kind of lies inside itself. So this disk is our domain, which is allowed. So we're going to do that. So we're going to say, so inside this modulus z is less than 1, which is our disk. That's a mathematical representation of what our disk is. Remember, centered at 0. Then we're going to have log of 1 minus z equals this power series. So notice that theorem A, all the conditions are met. F is analytic in that disk, or that domain, and that disk lies in that disk. So then, since all this is true, F has power series, this valid inside the disk. And so I've just substituted everything. I have sum A sub k is simply given by what I said down here, f, the kth derivative at z naught, over k factorial. So we have the kth derivative at z naught, which in this case is 0, since it's centered at 0, over k factorial, z to the power of k. Notice it's not z minus anything, because it's really z minus 0, because it's centered at 0. So I wrote it in this simpler form. Now all that's left to do is just clean this up a little bit. So let's expand this. Let's write the first term. What would the first term be? That would be if we plugged in 0 for k. It would be f of 0 over 1, and z to the 0 is 1. So all it really is f of 0. What is f of 0? It's going to be log, on the back side of this paper, it's going to be log of 1 minus 0 or log of 1. And log of 1 is 0. So that turns out that f of 0 just canceled out. We don't need to worry about it at all. We just need to worry about the first derivative, second derivative, and so on. So all we're worried about is what's in this parentheses here. This sum from 1 to infinity. Notice it's not starting at 0 because we just took care of that. From 1 to infinity of negative k minus 1 factorial over 1 minus 0 to the power of k times 1 over k factorial. And all those substitutions come from f, the kth derivative of 0, which is right here. So if we plug in 0 right there for z, we're going to have 1 minus 0 to the power of k, which is what we see right here. So then the other part comes from negative k minus 1 factorial, and that just went straight in here. Then we retain this 1 over k factorial, which is coming from there, and the z to the power of k. So now we can do some more factoring out of stuff, because if we have k minus 1 factorial over k factorial, we are just left with a k on the bottom. This negative sign is staying throughout the whole thing, and then we have this z to the power of k, which just shows right here. And 1 minus 0 to the power of k is just 1 to the power of k, and 1 to the power of anything is 1, so we don't need to include that. So final answer after all this dust clears is that log of 1 minus z, and notice that this is only true inside of that disk because that's where we defined it. It's not necessarily true anywhere else. Okay, so inside that disk, log of 1 minus z is equal to sum from 1 to infinity, and this should be k equals 1, of negative z to the power of k over k. So this seems very simple for such a complicated mess, but that's kind of the elegance of power series, because we can express these sometimes complicated functions as very simple power series. Okay, so let's talk about one more corollary and then one more topic and we'll be done. So the corollary that we want to talk about is, suppose f is analytic on D, which is how they kind of all start. And at some z naught, which is an element of D, the kth derivative of f evaluated at z naught equals 0 for k equals 0, 1, 2, and so on. What does that mean? That means that simply f of z naught equals 0, f prime of z naught equals 0, f double prime of z naught equals 0, and every derivative, if you take every derivative of f and you plug in z naught into it, it's going to be 0. So I've put that right here. So this is z naught right here. I'll draw a cleaner picture of this in just a second because this is confusing, but this z naught right here, this red dot, is going to be the z naught from this theorem, this corollary. And so if you plug in, if you take f of that point, it's going to be 0. If you take f prime of that point, it's going to be 0, and so on. You take every derivative. So what's the punchline of this theorem or corollary? It's going to be then f of z equals 0 for all z in D. And this is kind of the remarkable thing. This theorem basically says that if you have any point here where the derivative is 0, the second derivative is 0, the third derivative is 0, the initial function evaluated there is 0, then the entire function evaluated at any point in this domain is 0. So if you take some point right here, for example, and you take f of that point, that's going to be 0. You're probably asking, how does this point over here affect this point here or any other point in this domain? Well, that has to do with these little circles I've been drawing here. So here's how it kind of works. I'll draw a pretty simple picture. Let's say this was z naught. Okay, so this, since z naught is an element of D and f is analytic on D, we can have a disk, open disk, centered at z naught, and inside this disk, by theorem A, since that disk lies in D, f has a power series valid in that disk. So all these a sub k coefficients are given by what? They're given by the kth derivative of f evaluated at z naught over k factorial. But in the case here, what is the kth derivative evaluated at z naught? It's going to be 0 every single time, which means these a sub k are going to be 0, and this power series is going to be 0. So we're going to have f of z equals 0 inside that disk. So we established that within this disk, f of z equals 0. Now still, how does that affect things that are outside that disk? Well, we just kind of play this game again. Choose another point, preferably something that's pretty far outside z naught, but still inside the disk. So this blue point right here I've drawn is going to be a new point we'll call z1. Now notice that z1 is inside this disk, which means that f of z1 is equal to 0. Not only that, f prime of z1 is equal to 0, because if we take f prime of z, that's going to still be 0. F double prime still be 0. So that means that f prime of z1, f double prime of z1, the original function evaluated at z1, everything is going to be 0 at z1. So this is just another z naught. We can do the same exact thing. We can just draw another open disk like this, and we can apply the same logic and say that everything inside this open disk is going to have initial function evaluated there is 0, first derivative is 0, second derivative is 0. It's all true again. And using that method, sometimes very slowly, we can work our way around this whole domain just by drawing more open disks like this. So just to see how this might work, the last one I drew is this pink one right here on the very outside. So pretend I chose a point right there. So now I can draw a fairly large disk, and everything inside there is 0. Now let's say I choose this point right here. Now I can draw even a fairly larger disk, and this disk that I'm drawing actually encompasses this purple point that we initially thought had nothing to do with this original Z0 up here. Everything in this disk is 0. So that's how it kind of works. And using this, you can reach every part of your domain, and that means that the whole domain evaluated at Z0 is going to be 0, which is pretty crazy. Okay, so the last topic we'll talk about is order of 0. So we'll just go through it. It says, suppose f is analytic, no big surprise there, and not 0 on a domain D. So that means that f is not 0 on every single point on a domain D. There is some point where if you evaluate it there, it's not equal to 0. Now suppose f of z0 equals 0 for some z0 element of D. So that means that there is a z0 where if you plug in into f, it equals 0, but not necessarily f prime of z0 equals 0, just if you plug it into f. Okay, so that means that f of z is equal to a sub 1 z minus z0 plus a sub 2 z minus z0 squared, and so on. Why is there no a sub 0 there? Well, there would be. Well, there really is. In fact, a sub 0 is equal to f of z0 over k factorial, but f of z0 is what? It's equal to 0. So that means a sub 0 is equal to 0, and there is no constant term. So since f of z not equals 0. So also note that not all the a sub I can be 0, because pretend all the a sub I were 0. Pretend this one was 0, this one was 0, a sub 3 was 0, and so on. What would that imply? Well, that would mean, since the formula for a sub I is given by this, and k factorial is never 0, that means these are all 0. That means that f prime of z 0 equals 0, f double prime of z 0 equals 0, and so on. But can that be true? Well, what we learned on the back of this page was that if that were true, if it were true that at z0, f of z0, f of z0 equals 0, f prime of z0 equals 0, and so on, all those derivatives are 0, then f would be 0 on the whole domain. But what did we just say? We said that it's not 0 on the whole domain. So that means that not all the a sub I can be 0. So that means that there exists some positive number, m, greater than or equal to 1, such that maybe a sub 1, maybe a sub 2, maybe a sub 3, all the way to maybe a sub m minus 1 equals 0, but there has to be a first coefficient term which is not 0, and let's say that's a sub m. So that means that a sub m is not equal to 0. So then we can write this more formally. We wrote this up here as a sub 1, but really it's going to be f of z equals a sub m times z minus z naught to the power of m plus a sub m plus 1, z minus z naught to the power of m plus 1. And the reason for that is that we assumed that a sub 1 all the way to a sub m minus 1 are equal to 0. So a sub m is the first one. That's not 0. Okay, so I wrote in blue, not equal to 0. Notice that even a sub m plus 1 can be 0. These can all be 0, as long as there's one that's not. Okay? So the final punchline of all this is that the kth derivative of f evaluated at z0 is equal to 0 for k equals 0 all the way to m minus 1. And to see why this is true, take when k is 0. So that means f of z0 is equal to what? If we plug z0 right here, we plug it into all these places, and these are all going to be 0 to the power of something, and this whole thing is just going to 0 out. Now let's say we took the first derivative. Then how do you take derivatives of each term? You have to bring this m down, and this becomes an m minus 1. You do the same thing with this m plus 1. You bring it down, this becomes an m. So you do all that, and then you plug z0 in. Well, it's still going to be 0, assuming that m was not equal to 1, right? But the second that you get to the mth derivative, so let's say you get to the mth derivative, you want the mth derivative of f evaluated at z0, what's going to happen then? Well, after you take m derivatives, pretend, to make this idea clear, let's just pretend m was 3, okay? So after you take the first derivative, what do you have? You have m times a sub m z minus z0 to the power of m minus 1, or 2. Then when you take another derivative, then this exponent becomes 1. You take another derivative, so now you're taking your third derivative, then this exponent becomes a 0, and this z minus z0 to the power of 0, this just cancels out. And all you're left with is a constant term. You're left with 3 times 2 times 1 times a sub m. And this is just 6 times a sub m. And a sub m, what do we know about it? It's not equal to 0. Okay, so then we say that the mth derivative of z0 would, the mth derivative of f at z0 would not be 0, because it would just be a positive number, or not necessarily positive, it would just be a number. So it would be a number. It would be just 3 times 2 times 1 times a sub m, not equal to 0. And if that's all true, then we say that f has a 0 of order m at z0, which means that maybe f of z0 is equal to 0, maybe f prime of z0 is equal to 0, but there must be some number m so that the mth derivative of f evaluated at z0 is not equal to 0. So this seems kind of complicated at first. Run through it again if you want, rewind the video, but it's an important tool that we use a little bit later on.